Hi everyone. What I'd like to do right now is just to kind of review where we've come from and talk a little bit about where you are right now in terms of your hypothesis testing. My goal really is to help kind of tie everything together so that you can really understand how hypothesis testing by hand and hypothesis testing with SPSS are linked to one another. And so if you remember back to where we started at the beginning of the semester, we were talking about distributions of raw scores. And when we had enough raw scores that we could consider it to be a population, we would draw the population like this if it was a normal distribution and know that this was showing the distribution of x's with the y-axis telling us the frequency of those scores. And so this distribution then is defined, either we calculate it or we're told, by the mean, which is the measure of central tendency, and the measure of variance. And so when this is a distribution of raw scores, the mean down here is either going to be m if it's a sample, or mu if it's a population. And the distribution is defined by its variance as well, which is the spread or clustering, and that would be described by S if it's a sample, or by sigma if it's a population. Okay, and so once we knew that, I could ask you questions about where a particular x lays on the curve. And so I would say something like, okay, if you are renting an apartment and you get a puppy and you know that the average weight of the distribution of dogs of that breed is mu, and you know that the variance is sigma, or the standard deviation is sigma, then what's the likelihood that your particular dog is going to grow up to be a dog, an X, that is a certain size? And that size can be defined by a z-score. And once I know the z-score, I know exactly where that X lies on the curve, which means that I know what the likelihood is of getting an X that is that big or bigger. And so I look up in the z-table and I find out what the probability is of getting a score that's that big or bigger. Okay, so that's what we did when we were talking about x's. Then what we did right after that is that we moved on to talking about distributions of means. So we talked about a sampling distribution of means. And that sampling distribution is going to look similar to this, except that, of course, it's going to be thinner. And it's going to be thinner because its spread or clustering is now defined as standard error, whose formula tells you that you're going to reduce the standard deviation of your original population by the square root of the sample size. So it's still a normal distribution. It tends to be narrower as long as n is big. But in this distribution, we still know that the center is defined by something called the mu for the distribution of sample means. The standard error I've already shown you. And so once you know that, you can tell me things about the likelihood of randomly selecting a mean, not a raw score, not an X, but a mean, because this is a distribution of sample means, a mean that is this big or bigger. So you have a mean, and you know that that mean pairs up with some particular z. And so then you can tell me what's the likelihood of getting a z that big or bigger. Okay? After that, we moved on to talking about t-tests. And t-tests are also normal distributions that also have frequency on the y-axis. But what's different about a t-test is that to know exactly what the distribution looks like, you have to know degrees of freedom. Once you know degrees of freedom, you know that it's a normal distribution with some certain shape, and that shape is also defined by a measure of central tendency that is the mean of the distribution of sample means. And now you know that the variability, the standard error, is defined by, or estimated by, I should say, S divided by the square root of n. But these are all the same. You guys see that? So it's all a measure of central tendency, a measure of spread or clustering, and then the questions ask you, okay, what's the likelihood of getting a mean that is this big or bigger? And so we solve for t because that mean is paired with a t. We look it up and we find out what the probability is. Okay, Now, even though I just said that, when we did a t, we didn't actually do it this way because we were actually moving into hypothesis testing. And so instead of getting a t and then finding the p, instead of doing that, because the table doesn't work that way, you can look at it, it doesn't work that way. Instead of doing that, we would start by finding a t critical. And that t critical value is what determines a probability of 0.05 in the tail, because we want to set alpha to 0.05 for hypothesis testing. So given the degrees of freedom, right, knowing if it's one-tailed or two-tailed, so we know if we've got 0.05 in one tail or if we've got 0.025 in each of two tails, we look it up in the back of the book and we find a t critical value. Then what we do is we calculate our t, and all we have to do is find out if the t is in the critical region created by that t critical value. So if this is the critical value here, then if my t is bigger than the t crit, which is what sets off this region, then I know that my probability of getting a t this big or bigger is less than 0.05, and I would reject the null. So that's how we do hypothesis testing with a t-test. Now, the only thing that's different with SPSS is that SPSS, in a way, goes back to how we did it over here with x's and means and z-tests. Because when you run SPSS, SPSS, unlike your t-table, can determine the exact probability of a t. So when you run SPSS, instead of starting with the t-crit, which is how we have to do it when we do it by hand because all we have is the table, instead of doing that, SPSS actually finds out the probability of the t that you have, and then what you're going to do is you're going to compare that probability to our criterion of 0.05 to see if it lays in the tail. Okay, I hope that helps, but let me just say this one more way. For every distribution, whatever is on the x-axis, you can find that particular x or m anywhere on the curve. And for each of those x's or m's, there is, in this case, a z-test, which has a corresponding probability. In this case, a z-test that has a corresponding probability. In this case, a t that has a corresponding probability. And when you're hypothesis testing, what you want to know is if the probability of that t or that z is less than 0.05. And so you can determine if it's less than 0.05 either by comparing the probability to 0.05 or by comparing the t to a critical value that sets off the area of the curve that is equal to 0.05. Okay, I hope that helps. You guys keep up the hard work, and we'll be moving on to ANOVA in the next section. All right, thanks.